Hey, good morning. We're going to work on problem 935 from the 12th edition of the book here. We're supposed to find the moment of inertia of this shape, of the shaded shape, with respect to the x and y axis if a is equal to 20. So with respect to this, come on, you can do it. There you go, this and this axis if a is equal to 20. So remember, the moment of inertia is kind of a measure of how hard it is to rotate these things. It depends on if you're doing strengths or if you're doing dynamics. To me, that's a more intuitive sense. And again, it's a little bit of a lie. It's really the mass moment of inertia, but we're just going to go with the moment of inertia. And it kind of helps you make some decisions as we go through this. Now, for some reason, the solution manual does it with respect to this and this axis, which is, it's fine, but it's kind of odd because it's not actually what was asked. I'm not totally sure why they did that, but we're going to do the problem as asked. So we're going to do it with respect to the XY axis listed here. Okay, so what this is really, I was gonna draw this to scale, but just to fit this in a little bit, it's this big rectangle, right? But then you subtract off this kind of half circle that looks like a D when I write it like this, and you subtract off this other, and kind of a little bit to drive the point home, this other half circle that's on the other far side. And so I can call this body 1, body 2, and body 3. And so Ix and Iy are going to be the sum of those, or really it's going to be, so you're going to have Ix is going to be Ix1 minus Ix2 minus Ix3, right? And same with Iy. Let's do Ix first. Okay, so Ix of anything, now we're talking, so this big block right here, I'm going to that's what we're talking about, right? So it's equal to, so Ix1 is, from the table, if you actually look at the table, good old fashioned, rectangle. It's just we're going through the centroid, so it's just that 1/12 BH cubed, right? So 1/12 BH cubed. So in this case, it's going to be 1/12, and the base in this case is 3a, and the height is 3a cubed. And then once you plug in the numbers, that ends up being, so, well, I'm just going to put it in terms of a first, so because you end up with, no, I'll just plug it in. So 3 times 20, you're going to raise that to the fourth, and then divide by 12. So you get 1, let me put it in terms of e to the 6. So 1.08 times 10 to the 6 millimeters to the fourth. So that one's kind of unexciting. It's basically what you'd expect to see. Okay, and then I'm going to keep going. So Ix2 is, now we're looking at this shape right here. I'm not sure why the computer is freaking out like that. That's interesting. Anyways, let's see if we can do that. And we're going to look up the table lookup. And again, now we're looking at a half circle. Now this is where you have to be a little bit careful. The data is in here, but it's not going to be the Ix because this is rotated. So really we're looking for the Iy of this one, right? So we're looking relative to this axis, the axis that's going through there. But it turns out that they're the same. It's the 1/8 pi r to the fourth. So 1/8 pi r to the fourth. So in that case, it's going to be 1/8 pi times a to the fourth, or 20 to the fourth. So that is equal to 20 to the fourth times pi. That divided by 8. So that's equal to 62.83. 62.83 times 10 to the third millimeters to the fourth. Okay, so that was this body right here, right? So now we got to do this number 3. So Ix3 equals, now again, we're saying, I'm going to come back over to this one. Now we're looking at this one right here relative to this axis. Okay, and so if you kind of remember that, hey, this is kind of a measure of how hard it is to rotate around that axis, so to rotate it around like that, you'll notice this one and this one are going to have absolutely no difference because it's functionally it's the same axis, right? So mathematically, what are we talking about? Well, if we're going to come in here, I'm going to delete that so I can show off a little bit better. If I define the axis from here and here, then rotating around the y-axis won't be any different than if I define the axis, say, from like here or from here and here. This will be the same regardless, right? And so we can come in here and we can say, well, that is equal to IX2, which is a 62.83 times 10 to the third millimeters to the fourth. I mean, you could do the math again, but it seems unnecessary. And so, therefore, I'm just going to add them all up. IX is equal to the 1.08. So, this one up, 6. So I have to plug it in my calculator and then subtract them off. So we're looking at, so it's again, IX1 minus IX2 minus IX3. So that is equal to 954 times 10 to the 3 millimeters to the fourth. So I personally haven't built up an intuitive sense of the values, but it should be less than this, right? Because you're removing stuff from it, so it should make it even easier to rotate around that axis. So it's going to be less than that. And yeah, we're going with that. So there we go. That is our IX. So we have gotten as far as calculating IX of the whole system. And it turns out also, if you actually look at the solutions manual, when they do it through this axis, from here to here, it is the same, because again, this remains unchanged. Now the calculating IY are where things can change. So let's get into that. So again, we're going to say IY is going to be IY1 minus IY2 minus IY3. Okay, so let's look at IY1. So now we're talking about this body right here relative to that axis. So this is no longer 1/12 BH cubed. We can use a parallel axis theorem, or we can know that this is one of the few times where we just memorize the answer, or look up here, relative, you notice it says relative to this axis, and here I can zoom in, I think. There we go. It's 1/3 BH cubed, or 1/3. It's always going to be the base, the portion parallel to here, and the portion perpendicular to here cubed. So in this case, 1/3 BH cubed. Luckily, in this case, it's easy to not get lost because B and H are the same values, but it's this distance is B and this distance is H. But it's the same thing, so it's 1/3 times 3A times 3A cubed. So it's 3A to the fourth. So that ends up being 3 times 20 to the fourth. All that divided by 3. And that is 4.32 times 10 to the 6 millimeters to the fourth. Okay, so just as a quick gut check, this is a square, right? This is a square. I mean, so if we're looking at just this first term right here, the IX and IY, are they going to be the same? They're not, because IX is saying, hey, if I rotate this around through the center of that, it's going to be way easier than if I rotate it around from the back of that. If you are doubting that, grab a book anywhere that you have it, hold it right in the middle and kind of like rotate it around in your hands, and now hold it at one end and try to rotate it around your hands. It is significantly more difficult to do that. And mathematically, this number and this number show that. It is significant 4 times more to make that happen, and it's because of the parallel axis there. So now let's look at IY2. IY2 is, again, I'm going to erase some of this so as to make it a little bit easier to see. We're now looking at IY of this shape right here. So we're saying relative to this axis, how hard is it to rotate it around in that direction? Right? What is the IY of that direction? Well, it happens that we do still have a convenient table that we can look at, and we're going to say, hey, so now we're saying it's relative to this axis, right, because it's rotated, and we have an answer. It's right there, 1/8 pi r to the fourth. Life is good. Life is easy. So it's 1/8 pi r to the fourth, and it seems like we've done that already, right? It is this value right here. So that is IY2 is 62.83 times 10 to the 3 millimeters to the fourth. Okay, life is good until now. And then now is, and this is to me the reason this homework assignment is assigned is we need to be able to consider this last part. And I'm curious if you guys can see that. That's really weird. So IY3 is what? So now what we're looking at is this axis, this thing right here, relative to this axis. Okay, so this is an example of needing to use a parallel axis theorem, because I can't look at the table here and say, oh, clearly relative to, because it's basically like this axis right here, right? So that's just not one of the options, right? I haven't defined x and y. If in the table it had x and y and is exactly the right distance, life would be good, but that's clearly not a real thing. So I'm going to come in here and I'm going to say, well, IY3 is clearly IY3 bar plus the distance squared times the area, right? That is a parallel axis theorem. Okay, and so how do you move forward? Well, what is IY3 bar? Well, hey, I have a table. And I can say, what is, now again, we're looking at x because the table is rotated, right? So what is IX bar? Well, strangely, you will notice on this table, it is not there, right? So you'll notice on here, it's given on things like the triangle, you're given both IX and IX bar, right? And on the rectangle, same thing. But all of a sudden here, it's missing because X bar is that the X defined through the centroid, right? That is your X bar, Y bar values. So that is a little bit of a problem. So what do we do with that? Well, you cannot use parallel axis theorem with anything but the centroidal axis. And that's because, again, you get into the math, and it's because one of the terms goes away when you deal with the centroidal axis. And so the parallel axis theorem only makes sense to use if you're using the centroidal axis. So, well, what do I do about that? Well, I need to know what is IY3 bar. What is that? Well, I can look at any semicircle and say, well, again, IY3, I'm just going to not have the 3. I'm just going to say, well, IY is IY bar plus the distance squared times the area. Why is that helpful? Well, in this case, relative to this axis, I know what it is. That is given as in the table lookup, again right here, as 1/8 pi r to the fourth. It's like, okay, so 1/8 pi r to the fourth is, we're looking for this, IY bar plus the distance. Well, I do know the distance, right? The distance is going to be from the centroidal axis to that. Well, how far is that? That is a table lookup from the previous table from chapter 5 instead of chapter 9. And I'm going to look at that. And now don't make the mistake that I often make of switching between circles, arcs, and circles. But here we have 4r over 3 pi, right? And so the distance from the centroid is 4r over 3 pi. Now it's going to be squared. And the area of a half circle is pi r squared over 2. So therefore, IY bar is 1/8 pi r to the fourth minus, now here we're going to have, this is going to be 16r squared over 9 pi squared times pi r squared over 2. And so one of the pi's is going to cancel. This is going to cancel and make that 8. And so IY bar is 1/8 pi r to the fourth minus, and then 8 over 9 r to the fourth over pi. Piece of cake, right? So I say semi in jest. I don't know why they don't offer that up. But honestly, some of the textbooks do have that in the tables. But our textbook does not have that in the tables. But now I know IY bar. Now I can go back to my good old-fashioned parallel axis theorem. That's what I'm looking for. So I can say, therefore, IY3 is equal to IY3 bar, which is, hey, look at that, I have it. 1/8 pi. Now, R in this case is A, right? So A to the 4th. Sorry, that was really bad handwriting. A to the 4th minus 8 over 9 pi, A to the 4th. My A's and 9's are looking very similar. Okay, so that is IY3 bar plus the distance. Now I have to look at the distance, and this, again, it takes a second. The distance is from the axis that you care about, so in this case, this axis right here, to the centroid of that thing. So I need to know this is my distance right there. Sorry, that was not even close to a straight line. Well, again, I don't know that number, but I do know from here to here, right? That is a 4r over 3 pi. And I know from here over to here is 3a. So I can do this hopefully in a clean way. It's going to be 3a minus 4a over 3 pi. And that needs to be squared, right? Because that's the distance, that distance squared. All that times my area, which is again pi a squared over 2. And that is my I3. I mean, it's like the easiest one ever, right? No, it's actually, this is the reason this problem is important. Is if you look through the table, sorry, this is the chapter 5. If you look through the table, we're given the bar values right there on the triangle. We're given the bar values often, right, on a pure circle, but there are times when we're not. The quarter circle and the half circle were just both given the IX and IY, not the IX and IY bar. And so just make sure that you are using, if you're using the parallel axis theorem, you have to use the bar. So therefore, you'd have to calculate the IX and IY bar to be used for this. And then here, we plug this in, and then we actually, at this point, it's just a number. It's kind of all sorts of opportunities to mess up and do the math wrong, but it's just a number. So let's plug that in. And I'm going to totally cheat and pause the recording for a second so I can plug it into my calculator. And voila, a second later, after lots of plugging into calculators, I get IY3 is equal to 1.685, 1.68477. So 1.685 times 10 to the 6 millimeters to the 4th. So that's a pretty big chunk, which again makes sense, right? You start, so let's go back to looking at this whole thing. As this gets further and further removed, if you start making this block, bigger and bigger, you're removing chunks way out at the end. That has a big effect on what you're doing. And so that is our IY3. Again, remember, IY3 bar is only, it's necessary to, but it's not, it's just an intermediate step. It's not our answer, right? So now we have IY2 and IY1. So then we can just simply add them all up, right? So we have 4.32 times 10 to the 6th, and subtract off 62.83 times 10 to the 3rd, and then subtract off this 1.68 times 10 to the 6th, and we get IY3 is equal to 4.226 times 10 to the 6th millimeters to the 4th. Sorry, typo. When you subtract all this stuff off, you end up with 2.57 times 10 to the 6 millimeters to the 4th. And that is your IY. So zooming out just a little bit. Okay, so let's do a kind of a couple gut checks. Okay, so we removed, so looking back at the original thing, right? We're asking the IY and IX around these two axes. So again, high level, if you just think of like, if you think of this as kind of how hard is it to rotate around those axes? Ix, we get roughly 1 times 10 to the 6th, right? Just under, so 954 times 10 to the third. So that's saying rotating it around here has a certain kind of like mass to it, a certain difficulty. Now rotating it around here, you would expect it to be harder because it's further away. And yeah, it is actually further away. Now, removing these parts further away from stuff helps, if you will, right? Because you're doing that. But you end up with, I'm going to erase that so it's a little more readable, 2.57 times 10 to the 6th. And that is it. So again, the takeaway for me for this problem is that you got to realize that when you're doing the parallel axis theorem, you have to use the IY bar. In our book, at least, that is not given. So you're going to have to calculate that IY bar. So you're going to have to come through and make this temporary calculation of that. And then you're going to turn around and use that in here. Once you have this calculation, it's just a number, right? And so now you can just plug it into this equation just like any other time. But then you should be good to go. And that is problem 935 in a nutshell. If I can figure out how to stop. There we go.